All right, in this video I'm going to talk about partial fraction decomposition, which is basically an algebra technique to evaluate certain types of integrals. So I'm going to start off right away with an example. Let's integrate 1 over x plus 2 multiplied by x minus 1. So the idea of this is that we are going to take this fraction and decompose it, break it apart into something that we can then integrate. These problems are recognizable because you can break apart a denominator. So if the denominator is factorable, that's how you would know to do this sort of a process. All right, so what we need to do is break apart that denominator. So I'm going to ignore the fact that we're integrating. And so this is kind of a separate side problem here of taking what's inside the integral. And what we want to do is split this up into its possible factors in that denominator. So we have one factor of x plus 2, and we have one factor of x minus 1. And then the question is, what is on the top of these denominators? So I'm going to call the first one a and the second one b. And these are the things I need to solve for. Now notice I do have an equal sign. These things are equal. It's just if I took this fraction and this fraction and added them together, I would get my original. So what I'm doing instead of adding them together is I'm breaking them apart. I am decomposing them. Okay, so the next step, I am going to multiply both sides by the common denominator. That common denominator is the x plus 2 times x minus 1. So I'm going to multiply that side by that common denominator. I'm going to multiply this other side. I'm running out of room over here, sorry, by that common denominator. So on the left-hand side, the common denominator cancels. This should always happen. So on the left, I get 1. On the right here, for the a term, the x plus 2's will cancel for the a term. So then I will be left with a multiplied by x minus 1. On the b term, the x minus 1's cancel, and I'm left with b times x plus 2. Now where I'm trying to get to is I'm trying to solve for a and b. So if I chose x equal to 1, it would make this quantity right there 0. It would make a go away, and then I could solve for b. So I'm going to set x equal to 1. On the left-hand side, I have 1. A is going to be multiplied by 0. B would then be multiplied by 3. I'm going to plug in 1 and get 3. So that leaves me that B is going to be 1/3. Now I would want to choose another value for x so that I could make B go away and solve for A. And if I plug in -2, then I've got -2 plus 2, and that's 0. And it makes b go away. So I'm going to plug in, what did I say? -2 for x. So on the left I have 1. A is then going to be multiplied by -2 minus 1, that's -3. And then -2 plus 2 is 0, goes away. So this leaves me that A is equal to -1/3. So this process, notice I haven't integrated yet at all. The only thing that this process has done is decomposed that fraction. Now I can come back to that integral and rewrite it as its decomposition. We said that 1 over x plus 2 times x minus 1 was equal to this decomposition. I'm going to rewrite it with that decomposition in there. A times 1 over x plus 2. I wrote it like this because of the fraction. I wanted to write a out in front of that fraction just because a itself was a fraction. I could have written it on the top. Plus b, which is 1/3. I'm going to do the same thing here and leave it out in front. And you could even leave it out in front even if it wasn't a fraction. All right, and now I have something that is actually integrable. So for this first part, 1 over x plus 2, that's going to give me a natural log. A natural log of the absolute value. Because of domain issues with an integral of 1 over x or 1 over x plus 2, what is inside the natural log needs to be in an absolute value so that there's no domain issues on this integral. Plus 1/3 natural log of x minus 1. And then, of course, we'll add our c. So usually in these problems, the integrals themselves are not difficult. It's the decomposition where the work actually happens. Okay, so let's talk about different decompositions because that can be tricky, how to decompose this. I mean, I put A and B on top of these, but there was a reason for that. So let's just look at what would have happened if we had had 1 over, let's do x squared plus 2. Remember before I had x plus 2. So if you had a fraction like this, you would want to break this into ax plus b over x squared plus 2, and then another quantity c over x minus 1. So what happens with every decomposition is that what is in the numerator is going to be 1 degree less than what is in the denominator. So here in the denominator, I have my degree is 2, so in the numerator, my degree is 1. Here in the denominator, my degree is 1, so in the numerator, my degree is 0. Anything to the 0 is 1, so c is essentially multiplied by 1 right there. So moral of the story here, if you have a 1 in your exponent, you're just going to have a letter in the top. If you have a degree bigger, then what is in the top is going to be 1 degree less. Okay, so that's kind of one of the rules. Now, another thing that can happen is that instead of just having, this is what we started with our example, but instead of just having one quantity of x plus 2, maybe we could have 2 quantities of x plus 2. What happens here is that the degree is still 1, so we still have an a over x plus 2, but that x plus 2 has a multiplicity of 2, and so we're going to need another quantity over its multiplicity, x plus 2 squared, and then we still have that x minus 1 in there. Right, so notice on this one, degree is 1, degree is 1, degree is 1 in all of those denominators, and that is why it gets a degree 0 in the numerator. It just happens that this has a multiplicity, and so we need as many terms as that multiplicity. If that were a 3, we would have another one right in here with an x plus 2 cubed in the denominator and another letter in the top. Okay, let's see. We also need to look at what would happen if we had, say, for instance, 1 over x squared times x plus 2 times x minus 1. Now this one's tricky because, maybe not tricky, but if you look at the x squared, that's what's different here. The question is that a degree 2, or do we consider that to have a multiplicity of 2? And the answer is essentially either. You would get the same exact thing. I consider it to have a multiplicity of 2. That's how I think of it. So for the x squared part, I would write that as a over x. There's my first one. It has a multiplicity of 2, so it's going to get another letter over that x squared. The other ones are still single ones. Those would just get their single letters over that term. So c over x plus 2 and d over x minus 1. And just notice on this that if I had wanted that x squared term, if I had considered that to be a degree 2, I would have written ax plus b over x squared. If you divide the x squared into the ax, you get a over x. And then you would divide the x squared into the b, so we divided the x squared into the a term, divide the x squared into the b term, and we get b over x squared. See, same thing I got us up above. So what I'm saying there is it doesn't matter how you deal with that x squared. I think the way that I think of it with the multiplicity, the multiplication later on becomes a little bit easier if you write it out like that. And one other tricky thing that can happen is, let's say that we've got 1 over x plus 2 times x squared minus 1. Now this one, I'm sort of tricking you here because it looks like it's a degree 2, but it's really not because it's not yet completely factored. That x squared minus 1 can get broken into x plus 1 and x minus 1. So in this example, just keep in mind that, that the denominator has to be completely factored before you split it up. A to x plus 2 plus b over x plus 1 and c over x minus 1. Okay, so I've now kind of gone over all the different types of decompositions. You can either have a degree that is higher than 1, or you could have a multiplicity, in which case you will have the same number of terms as that multiplicity. Here's an x squared with multiplicity, or it cannot be completely factored. So kind of your first step is make sure it's completely factored, then split it up. Okay, one more example. Let's look at the integral of 3x squared plus 9 all over x cubed plus 9x. Okay, so now, first of all, this one is not completely factored yet. So let's do that. So in the denominator, these have an x in common. So I'll factor out an x, and I'm left with x squared plus 9. And this was all over 3x squared plus 9. Okay, so x has a multiplicity of 1. So that will get an a. X squared plus 9, that has a degree, I'm sorry, with the x, I think I just said multiplicity and I meant degree. X has degree 1, it gets an a. X squared has degree 2, and so it is going to get a degree 1 polynomial in the numerator. Okay, so my next step is to now multiply by the common denominator, which is this denominator on the left-hand side. So on the left-hand side, it will cancel completely. I'll have 3x squared plus 9. On the right-hand side, for the a term, the x will cancel, and so I will be left with a times x squared plus 9. And for the bx plus c, the x squared plus 9 will cancel. And so that will be multiplied by x. I know I did this pretty quickly here. I definitely understand if you need to take an extra step of actually writing out, make some parentheses there, write out the multiplication, look at what cancels. Now, choosing x's, like I did before on this one, doesn't work so well. So I'm going to show you another way to do this next step. Remember before we chose x equal to -1 because it canceled the a term, and x equal to, or maybe it was 1 and -2, I can't remember the numbers, but they canceled. They would make one of those terms essentially 0, but even if you look at this one, there's no x's that we can choose to make that 0. And even if we did, that leaves us 2 things here to solve for. So it doesn't work. So what I'm going to do is multiply everything out. The left-hand side is obviously all multiplied out. I'm going to leave it as is. So on the right-hand side, we get ax squared plus 9a plus bx squared plus cx. Now I'm going to make some equations. I'm going to look at everything out in front of the x squareds and make an equation out of that. I'm going to look at everything out in front of the x's. And then I'm going to look at everything else. I call those the numbers. So if I look at everything in front of x squareds, I've got a 3 on the left, an a and a b on the right. So I've got an a and a b, a plus b on the right, and a 3. So I took out the x squareds. I'm just looking at the coefficients in front of them because whatever happens on the left with x squareds has to happen on the right. Same thing with the x's. So if I look at the left, well, let me look. I wrote this kind of the opposite way around. So let me look at the right-hand side here. I have a c out in front of those x's. And if I look at that c in there, let's see here. You know what? I would like to, I'm sorry, I'm going to do this, but I'm going to change this problem. I'm going to make this 3x squared plus 9 plus x right there. I'm just going to add an x right there, which is going to add an x right there and add an x right there, and that's going to make that c equal to 1. And then I want to look at all the numbers. So on the, let's see, what do we have left over? So I'm looking over here. We've dealt with x squared, we've dealt with x squared, we've dealt with x's. I've got a 9a left over. So I have a 9a left over there. And on the left-hand side, I've got x's, I've got a 9 left over. Okay, so that means that a is going to equal 1. And if a is equal to 1, put that back up there, b is going to equal 2. Okay, so I've got a equal to 1, b equal to 2, and c equal to 1. Okay, so what I'm going to do now, let's see, do I have enough room to rewrite this? I think I do, just enough. So I'm going to rewrite this integral with everything split up. So a was 1, that's over x, and by split up I mean it's decomposition. I'm rewriting it like this, but with a, b, and c in there. Plus, b is 2, c is 1, it's all over x squared plus 9. Now this I am going to have to write as the integral of 1 over x. And if we look at this integral and sort of think about it quickly, maybe a u substitution might work. But then du would be 2x, and we have this 1 that's causing an issue. So you could try and play with this integral, but it's not going to work as is. It has to be split up. That x squared plus 9 needs to divide into the 2x. I'm going to make this a different color. So it needs to divide into the 2x over x squared plus 9. And it needs to divide into the the 1. So we'll be left with 1 over x squared plus 9. dx. Okay, so now 1 over x. Well, that's not so bad. That's just natural log of absolute value of x. Now, this next one has this 2x in the denominator. So I'm going to come up here on this kind of upper part of the paper and look at this guy. So in order to do this one, if I set u equal to x squared plus 9, then du would be equal to 2x. And so then for that one, I would be left with the integral of, well, we've got a 2x on the top of this one, and we've got a 2x there, so I'm just left with 1 on the top of it over u, which is natural log of absolute value of u. And now I can bring that back down, add it to my natural log of absolute value of x. So for that next one, I'm going to get natural log of the absolute value of u, where u was x squared plus 9. Now the next one. We'll do that in green over here, kind of right up above it. So now this one doesn't have the 2x in the top. And if you remember, we had that integral of inverse tangent, but for that one we needed a 1 instead of a 9. So this is going to require us to factor out a 9. And then what I would be left with is an x over 3, all that squared plus 1. Now the reason I factored out the 9 is so that I could get a 1 right here. We need a 1 right there in order to use that integral with inverse tangent. So now if I pick u as x over 3, then du is going to be 1/3 dx. So for this integral now, I still have that 1/9. For my dx, that's going to be multiplied. So if I think of just having dx, so I think of multiplying by 3. So then dx is equal to 3 du. Let's put the du way over here. And then I've got 1 over u squared plus 1. So this guy is then, that integral is equal to 1/3 inverse tangent of u. And now let's bring that back down to the bottom. So notice on all of these that I sort of did this extra work on the side, and I understand that you don't have colored pencils all the time to kind of show that you're doing that, but really when I write this out on my paper, I would have this work first, then I'd write out my integral, and then on the side of my paper, I might even box these guys on the side of it just to show my kind of extra work. All right, so where was I? I've got to fill in this green integral. So we figured out that that was 1/3 the inverse tangent of u. And u, in this case, was x over 3. And then I've got to add c, and there we go. Okay. So kind of a little synopsis here of this one. I'm sorry I had to change that, but I wanted it to have that value of c so that we could then split up this integral. I wanted to show you how that worked. So, so we decomposed. We had a degree 2, we needed a degree 1. We multiplied by that common denominator, multiplied everything out, looked at each one of the terms on each side, made an equation out of everything in front of x squared, an equation out of x's, an equation out of numbers, and we solved all of those for a, b, c, which was then plugged back into the integral. We had to split up the second integral into two, and then we had to do some side work on each one of those two integrals with a separate u substitution for each. And now we get our final answer. Okay, and I think that is it for this video.